everyone, this is Mrs. Guzman. These are your notes for simple harmonic motion. Before we can understand what simple harmonic motion is, we first have to understand what periodic motion is. Periodic motion occurs when a vibration or oscillation repeats itself over the same path. So we saw in the lab the spring bouncing up and down, and we saw the pendulum swinging back and forth. This repeated pattern of motion is a great example of periodic motion. So simple harmonic motion is just a specific case of periodic motion. If we had a spring that had a mass attached to it and the spring was oscillating back and forth, so at different points the spring is compressed and then stretched, where it normally would like to be, where it is at rest, so if the spring were just sitting on a table, we would refer to that point on the spring to be its equilibrium position. So this is where it rests naturally. When it is oscillating back and forth, you see it pass through this rest position. At that point, there's no force in the spring and there's no displacement of the spring. So you can see from the animation at 0, the equilibrium position, there's no restoring force and there's no position, which is really displacement. As it compresses though, the restoring force is in the opposite direction of that displacement. So the restoring force would like to get it back to equilibrium, so it will always point to that direction. As the spring stretches, this restoring force is still in the opposite direction of the displacement. So for a full oscillation, we'll see these two variables change direction. They're always opposites of each other though. So we measure one oscillation. You can also think of it as a cycle from one spot back to that same spot. So it is one complete cycle. So in this case, we're going to measure an oscillation from -1 and then back all the way to -1. You can choose any point to start as long as you measure back to that same starting point. The time that it takes to do this is what we refer to as the period. Period is abbreviated with a capital T instead of a lowercase t, which just means a time interval. So T, period, is a specific time interval, and it is the time it takes to complete one oscillation. We usually measure it in seconds, but it could be any time unit that we use. Frequency is a term that you'll also hear with simple harmonic motion, and this describes the number of oscillations per time. More commonly, the unit that we use for frequency would be hertz, abbreviated HC. And inversely related are these two variables. So period and frequency have an inverse relationship. If you know one of these variables, you can easily get the other one by taking 1 divided by the variable that you have. Hooke's law is used to describe this relationship between the restoring force and the spring's displacement. In equation form, it is F equals -kx, where F represents that restoring force in newtons. K is what we call the spring constant, and this measures the stiffness of a spring in newtons per meter. So the harder it is to compress or stretch a spring, the higher spring constant value that we'll have. If the spring is easily compressed or stretched, that means that it has a low spring constant value. X is the displacement of the spring in meters, and this is measured from that equilibrium position. We can determine the period for a spring using two equations. So period is T, it equals 2 pi, and then the square root of the mass. And this mass is what is oscillating on the spring. So if you think back to our lab, we added different masses to our spring. That's the mass that we would plug in for M in this equation. And then K represents the spring constant. Another commonly used equation for determining the period for a spring is T equals 2 pi, and then the square root of X over G. X, like in Hooke's law, is the spring's displacement, and G simply means gravity. So we would plug in 9.8 as long as we were working with problems that dealt with springs on Earth. A pendulum has a different formula for determining the period. but it is very similar. So the period for a pendulum is dependent only upon its length. So we should have seen this in the lab. As long as we're dealing with pendulums that are on Earth, gravity would be constant. So that's not really going to impact us unless we have a problem where we're maybe not on Earth for some reason. But really we are concerned about the length. So in this equation, t equals 2 pi the square root of L, which is the pendulum's length from the pivot point to the center of mass of the object attached, and then divided by gravity. So notice that there's no mass or angle in the equation. So those were the other two variables that we tested in the lab, and we should have seen no relationship for those two in our graph.